All right, my name is Harrison Leary, and this is my Physics Lab 1 on constant velocity. So for a brief introduction, the purpose of this lab is to compare the predicted and measured change in position of an object over time, and to look into how and why those values would not necessarily be the same. So the physics principles for this would be first Newton's second law, which is the momentum principle shown on the right, as F bar equals the change in, or the derivative of momentum over the derivative of time, which is also equal to mass times acceleration. And then also the velocity and position update formulas, which again are shown on the right, as Vf equals Vi plus F net over m times delta t, and Rf equals Ri times V average times delta t. Then with the system and surroundings in this experiment, the can, which will roll in the following video, is the system, and the Earth is acting as the surroundings. So with the experiment here, some initial values. The initial time is 0 seconds, and the initial position is 0, 0, 0 on all three axes. And the initial velocity is 1.932 meters per second in the x direction, and then 0 in both the y and z direction. And then for the video, here is what was put into the tracker. So I used the tracker to slow down the video and then try to pinpoint the center of mass at every frame so we could measure the change in position over a uniform amount of time, being 0.033 seconds for every snapshot. And then on the top right, you can see the measured values, which show a pretty strong correlation between the change in position and the change in time. Then here is my code for the theoretical half of this lab. So on the left, the only things I changed from the sample code were the on line 36, the ball.vel, which is the initial velocity. I updated that to my measured initial velocity of 1.932 meters, or meters per second. And then at line 49, I changed it to when time is less than 1.133 seconds, as this was the last recorded time value on my experimental measurements. And then I updated the formulas on lines 58 and 60 to the velocity update and position update formulas that were discussed earlier, but put into the form of code. And that resulted in this video. So as you can see, the ball moves at a uniform rate. The velocity is not changing, but the position is changing at a constant rate. That is the constant velocity. And it looks pretty similar to the following values. So you can see on the blue side of the graph, we have the predicted position, which was the theoretical in the code, and then the measured position, which is the actual can rolling in the experiment. So they change it at a very similar rate, but the measured change begins to slow down, and the most likely cause for this is the force of friction acting against the can, but it could also be that the tracker for each frame was not placed accurately at the center of mass of the can, which can cause a slight discrepancy between the values. Then for the post-lab questions, for the first question, flipping the axes would result in a change in the direction. If you were to flip the axes, whether it's flipping the x-axis or the y-axis, that will just multiply your values times a negative. And then for scaling the axes, that would also just scale your change in values, but they would stay at uniform relatively. And then for the second question, for the net forces, in the x direction, there are two forces acting. There's the initial applied force applied on the can by pushing it, and then the reciprocal force of the force of friction, which is acting against the can and canceling that out, which then creates a zero net force at that moment. And then later it would be the force would be slowing it down, which is what was shown. And then additionally, the gravitational and normal forces are acting down and up respectively, which also creates a net zero force in the y direction. So that's all. Thank you.